So I'm Mike Petullo. I'm from the United States Military Academy, which you may know as West Point. We teach undergraduate students, and one of my students, Joseph Suh, did this work with me. Unfortunately, he wasn't able to come because he had some obligations with his summer training, so he might be in the woods somewhere right now. I'm not sure what he's up to right now. So, as the introduction said, this is follow-on work to what was presented last year, so I'm going to kind of glaze through the introduction, and you can refer to that paper if you're interested. It's on the generality of convenience of Etypes. Let me just try something out on you, something I come up with this morning. So, you know, this will probably end up being a rather light talk, but I hope some of you at least find it kind of interesting because we're looking at it from the point of view of the operating system as operating system designers. But just let me try something out with you guys. I would just say that our operating system is somewhat LangSexy. All right? Maybe that's a new adjective we can start using on things. I'm not sure. Okay? All right. So where do we start? Sometimes, you know, if I see that in the literature somewhere, I'm going to have to take credit there, but maybe I won't see it. Some time ago, John Stroh started a project, and he was looking at really crafting OSs that really encourage secure applications. Of course, we have a lot of OSs that perform various authorization systems and whatnot, but really when it comes down to the OS is there to run applications, and we want to do what we can to make writing robust or secure applications easier. Okay. One of the intuitions behind Ethos is that, so the idea is that OSs provide a property called complete mediation, where the application can't really do anything out of its own memory space unless it goes to the OS's system calls. Okay. So one of the intuitions of Ethos is we leverage that property to try to improve security. Okay. We've been leveraging complete mediation to improve reliability for some time, really since the 70s, decades. And I'll give you an example, right? So the fork system call, right? You invoke fork, and then what's the API after you forked to get your memory isolated, right? Of course, there's no API to isolate your memory after you fork because the memory isolation is baked into the fork system call. It's in the semantics of the fork system call itself. So we kind of look at, well, are there other semantics we can draw on the OS so the application don't have to worry about them, okay? And sort of this LangSec type idea that every input should be recognized before it's actually acted upon is something we're trying to pull in the OS. So that kind of summarizes what we're trying to do with Ethos. Other things as well, encryption and other things, but I'm going to focus in on again, the LangSexy part, right? So the way this sort of works out is in Ethos, programmers, they declare the types of all the OS objects. So OS objects being files and network connections and interprocess communication channels. Everything in Ethos is typed. And essentially what happens if you imagine we have a program that happens to be written in Java, does a write system call. Of course, that needs to pass through the kernel. And since we've typed all our interprocess communication channels, for example, that gives Ethos the opportunity to recognize that information before it ever becomes input for this second program that happens to be written in C down here, okay? So the idea is that, you know, we kind of talked about earlier that we should be able to point our finger at where our recognition routines are as opposed to where our logic is. And I will tell you that in Ethos, the recognition routines are right here. I can point at them every time. They're in the kernel. And no data flows through the system unless it's been recognized, okay? So, you know, we might have other writes and reads going on. They might be going out the network or going to files. Whatever it may be, they're going to be recognized by the OS before they pass it along. Otherwise, the write or the read will fail. So we presented the details of how Ethos actually pulls this off last year at LangSec. Okay, so you can see that 2014 paper there if you'd like to. Okay, so before I move on, I'm just going to introduce 4 components from kind of last year's paper that are important for this talk. The first one is this thing called e-notation. And what e-notation is, it's essentially a type interface description language. This is where you describe the types that are going to be permitted by the system. Okay, so it's partially describing types and then also interfaces because we roll RPCs into the system as well, remote procedure calls. Corresponding to e-notation, there's something called encoding, and that's just the wire format, okay? So there's a single wire format for anything I declare using an e-notation. There's a corresponding encoding that would be used within the system, okay? But the other 2 things are 2 tools that you use during development. The first tool is called ET2G, and what ET2G is, it takes some e-notation specifications, and it essentially compiles that into machine-readable description of the types, okay? Because the OS has to be able to read those types in so that it can recognize them. And then also during this process, it produces what we call a type hash. And all a type hash is it's a universally unique identifier or name for a type, okay? And that's what you essentially associate with a file system object. So if you want to say that this network connection accepts integers, right? You would get the type hash for an integer, and you'd associate with that network connection or that file, much like you do with permissions today, okay? So you can think about it like metadata that describes the OS objects. The other tool up there is called EG2Source, and what that does is it takes a type graph as input, and it produces procedures, okay? So this is kind of the LangSec type of a deal, again, where we're specifying our types and machine generating, encoding, decoding, and recognizing routines, so we don't have to write them by hand every time, okay? They're automatically generated for us. And these routines that are generated, they're made use of both in the kernel and in user space. And you can, of course, generate routines for any programming language that you sort of write the tool to support, okay? Okay, so we've written a number of applications for this system. We've got a shell, some system utilities, some network utilities, a messaging system and whatnot, and that was the case last year. But what we wanted to show is basically that this system was general enough and convenient enough, okay? The reason it needs to be general is because it's universal. Nothing flows through the system unless it satisfies some e-notation. So is an e-notation general enough that we don't want a class of a certain set of programs that we can't write because e-notation doesn't sort of support them, okay? So today we're going to talk about how we think it's general and also convenient. So why does it need to be convenient? Well, it turns out that yes, Ethos does recognize all the types flowing through the system, but the problem is a programmer could, of course, say that his program just sends strings around the system, and then he could encode whatever he wants as a string, and at the other end, parse that back out and act on that data, right? So now we're back to where we started, where the system will recognize, yeah, that's a string, but in fact, it might be a rather sophisticated data structure, and the system is once again not helping us make sure that it's properly recognized, properly formatted, or well-formed with respect to some definition, okay? So we want to avoid this, and really the only way we can avoid that is by saying it's more convenient to use the system than to try to build yourself a loophole like this, okay? Okay, so I'm sure we're all familiar with the chart on the left. But we're going to start by talking about generality, and before we get into that, we're just going to make some comments on input languages, but I don't think this will be a surprise to anybody in the room, okay? So one thing is it seems that context-free grammars are kind of sufficient for most input grammars, okay? We do see systems, there's higher levels of competition we want to avoid. We do see systems that use context-sensitive languages, but oftentimes that kind of appears accidental, okay? So we know that Bacchus-Naur form can express context-free grammars. We know that there's a particular form of Bacchus-Naur that is called Chomsky normal form that is no less expressive as BNF, but it's a lot easier to transform. Okay, so we're gonna make use of that as we talk through this generality. Again, Chomsky normal form is nice because although it kind of blows up the number of projections you have, it's easier to transform it because it's so simple. So we're going to use that as a foothold as we get the system kind of going. And so what I'm going to show you is basically that we can machine process a relaxed form of Chomsky normal form into e-notation, and thus essentially show generality. That e-notation is basically equivalent to being able to say, I want any context-free grammar as my input, okay? Okay, so what we did is we wrote a tool called BNF2ETN. Joseph did a lot of the work here. It's written in Go, uses Nex and GoYak. And what it does essentially, it takes as input a grammar G in this relaxed Chomsky normal form. And when I keep saying relax, well, here's a relaxation. So I'm sorry, I should have gone back just to, of course, Chomsky normal form has three forms. The start symbol can go to the empty language or the empty string. The other two forms is whatever everything else takes place is you got a non-terminal can go either to two non-terminals that are distinct, or a non-terminal can go to a terminal. Our relaxation is essentially that center form where we say that a non-terminal can go to any number of non-terminals, and in fact, you can have the same non-terminal appear more than once on the right side. Okay, and that's sort of a convenient bridges the gap of some of the downsides of Chomsky normal form in a more general eBNF, although no more expressive, okay? Okay, so we take a grammar G as input, and what do we output? Well, what we output is types defined in e-notation, so we output e-notation, and essentially these types are sufficient to describe any syntax tree which follows from any statement which is legal under G, okay? So now we have an E notation that sort of represents our original grammar. And then we can process that, as I said before, to produce a type graph, type hashes, and then eventually produce encoding and decoding routines and recognition routines. Okay, we'll describe the output a little bit more in detail in a moment. So this kind of also, you know, aside from showing it's hopefully general enough for all inputs that we want to handle, it also shows that it's convenient, right? Because if you think about it, it's often easier for a human being to look at some eBNF. If you were to look at the eBNF for HTML, you're going to recognize exactly what it ought to be doing faster than perhaps if you looked at the parse tree that results from parsing it or something like that. So I think it makes it convenient for the programmer to be able to look at eBNF, even if it eventually turns into something like e-notation and then automatically generated routines. Okay. So again, it should be no surprise what this tool does. It lexically analyzes the grammar. You know, that is, it's actually looking at the Bacchus noun form describing the grammar as opposed to we normally parse some statement under the grammar. It's actually looking at the grammar itself, lexically analyzing it, producing a parse tree, and then analyzing that parse tree to generate e-notation. Okay. So what does it actually generate? It basically generates data structures, and the data structures take one of three forms, either unions, type defs, or structures. And there's three transformation rules that we're going to look at right now that actually do the work to produce this data structure that sort of represents the grammar. Okay. So there's three forms, three transformations, and this is the first one. This applies when you have some non-terminal on the left side more than once. Okay. So here we have A, and it appears 2 times on the left. You know, either A can be the terminal uint64 or A can be essentially BC. All right. And what we do when we see that is we generate a tagged union. Okay, and we call that union A, and it's got 2 options. The first option is the uint64, and the other one is the BC. Okay, so I should take a moment to describe what we're looking at here with the terminals. Okay, so in this process, terminals are a little different than what we normally think of. Normally, you think of a terminal, for example, if you're writing a parser for C, a terminal might represent a single digit, and then you might build what is a valid integer or something out of those terminals, perhaps using a regular expression or whatever your grammar tool supports. Okay. But here, a terminal isn't a terminal in that sense. A terminal is any type that's already known to the system. Okay, so uint64 is a built-in type, but this could just as easily be, for example, B, because presumably we're going to later define B. Okay. So one of the interesting things this does is it gives you some kind of estimation of what you sometimes get from context sensitivity. So the reason I say that is because I could replace this uint64 with a tuple of uint64s, okay? And the corresponding encoding of that would be a length followed by a number of elements, okay? And if you think about it, the element could even be any type that I've declared, so it could be a compound type and whatnot. So this is sometimes what the context sensitivity you see in networking protocols and whatnot, and so we can kind of indirectly support that through this mechanism. Okay, so the next form, and I guess I'm sorry, just to go back to the terminals. In a certain sense, terminals are less important. You know, you think about sometimes terminals are things like while, and really while is just letting you know something about what is to follow in the statement. And once you have your syntax tree, it's less important. And since we're actually building syntax trees, the other traditional use of terminals is less important. We can distill what things are based on the tagged union instead, as we're processing on the client or the recipient side. Okay. All right. So there's another. The very simplest transformation rule is essentially if you've got some non-terminal D which only appears once, then you just essentially create a type synonym or a type def. Right. So here we have a statement D can become only nothing but uint64. And then we just declare, okay, D is a uint64. And the same thing here, E becomes an FG, and so E is kind of type def to be an FG. Okay. So the final transformation rule is that 2 or more elements appear on the right side. So this statement here would not only trigger this rule, but would also trigger this following rule. And in this case, you just create a structure, right? Here we have H goes to IJ, and we create a structure. We name it IJ. And the fields of the structure just correspond to any number of non-terminals that appear on the right side of that production. Okay. So you can imagine if you start putting all this together, what you basically get is a data type that's able to represent any syntax tree of the grammar that you've started out by describing. Okay, and again, using the tag unions, you can kind of start to pick that thing apart on the other end once you've received it and act on it. Okay, and so to kind of put that in another way, if you think about, again, this is N, the E notation that comes out to be BNF2ETN. Here's the grammar that comes in. Essentially, any data that's well-formed with respect to N is a representative of some statement under G. And any statement under G can be represented by some well-formed instance of N. Okay. So here's an example of what it all kind of comes together. All this is at the top we have some BNF that represents an arithmetic operation in our relaxed Chomsky normal form. So you can see we take advantage of the relaxation right there to make it easier for a human being to kind of look at. We run that through BNF to ETN, and as output we get this E notation description. And if you read the previous paper, it describes quite a bit about what E notation supports. You know, it supports kind of the union of all the types you typically see in programming languages. Okay, the less sophisticated, less sophisticated type system languages. Okay. So we in the paper we talk about how we created a hyper, which is essentially a HTML-like grammar and a corresponding client and server. And if you're interested in that, you can look at the paper, or eventually get the source code. So this is what our programming flow looks like now. If you go through the technique that I just described, everything after BNF2 ETN is the same as it was last year, but just kind of to summarize what we did. What you do is you first specify your communication grammar using BNF. Then you feed that BNF into BNF2 ETN to generate the corresponding E notation types. And again, this is where it picks off from where we had before. Use ET2G to generate a type graph. The type graph contains machine readable description of the types and some type hashes. And then you can use EG2 source to generate some source code, which is your encoding, decoding, and recognition routines. You combine that with your logic code that you wrote in your programming language, and then you have your program. And then separately, you take those type hashes and you sprinkle them across all the file system objects that you want to permit the reading and writing of this particular grammar or type during the operation of the system. And from that point on, this program can only produce, using those OS objects, data which is well-formed with respect to this original grammar. If it's not well-formed, when it does the write will fail. Okay, so that kind of gets through generality. You know, we showed that it's roughly equivalent to context-free grammars. But we still have this problem. As you recall, the programmer who decided to just declare all his OS objects as handling strings and then basically encode everything to strings, and on the other side, parse it out, thus bypassing the OS's ability to really recognize what's really going on, okay, as opposed to just looking at strings. Okay, but there's some incentives within Ethos so that he won't do that, okay? The first thing is, right, you'll note that he doesn't have to write any lexing, parsing, or encoding routines, right, because they're all generated for him. In fact, typically there's not really any parsing going on. Instead, it's passing around these binary representatives in a well-known format encoding, okay? The next thing is the idea that you automatically get a formal documentation of your communication formats because they're in E notation, okay, and everybody's generating routines that handle that in machine-generated form. So if you think about packet types or some other things where they try to unify the documenting of the protocol with the actual writing the code for the protocol, okay, you kind of get that out of this. And then the final thing is that the routines that are generated resemble existing routines that everybody's really kind of comfortable with using, right? So on the left we just have an exemplar there of Python render stake. So it's just a library of expressions that you can compose to create HTML. In this case, you're just making an ordered list, a bunch of list items. And then on the right, we have the routines that EG2 source generated in a certain case. And you can see you're just sort of composing these things as if they're expressions, as you did with your Python render snake. So I think there's a lot of reasons why people would just like to use their system. They don't have to write any parsing routines anymore, or at least hopefully not as much. Okay. All right, so that sort of concludes here. Just to summarize, the key point, which goes back to last year, is that our goal is so that the OS itself recognizes all data before it ever serves as input into an application. Okay, so we're kind of leveraging the idea of complete mediation in the OS, and we're kind of declaring the types of all our OS objects so that is possible. So we've shown you that E notation can specify a data structure that's basically equivalent to a context-free grammar. And we've also shown you that incentives in Ethos kind of discourage cheating the system by just declaring everything as a string. Okay. So we have some future work. This is kind of work in progress. We're going to continue to work with our students on this. But one thing we really want to do is continue on the BNF2 ETN compiler so that it doesn't have to use this restrictive Chomsky normal form. We'd like to just blow it up to support eBNF. And the reason why that's a benefit is because, there's fewer productions, but more importantly, you can write the productions that a human being can look at and be comfortable with, as opposed to when you constrain what BNF is supported, then you end up sort of kind of jamming something you'd like to write it another way into the Chomsky normal form. On the flip side, then, by more closely resembling straight eBNF, your resulting e-notation will also be easier for a human being to kind of look at and be comfortable with what each subtype represents, or what each type in the composite types represents. The other thing we think would be interesting is a new programming language or preprocessor, which takes a program which is intended to run Ethos, and not separate from just the programming process. It compiles that program to object code, but also extracts all the types and does the type graph compilation, and then provides you with all the type hashes you need. And so that would kind of reduce some of the steps here where you have to use multiple tools in addition to your actual programming language. All right, that's not unlike how some, and everything back to ONC-RPC. Sometimes people they don't want to leave their programming language to have to write the other, in ONC-RPC's case, the other language that defines their interfaces and their RPCs and stuff. Okay, we're really working hard to get this open source. It's available, and you can see our website there. Again, John Solworth at the University of Illinois at Chicago kind of leads the project, the Ethos project. You can contact him, and he'll give you access to the source code now. But we're trying to push out an open source release this summer. The reason why I say it's a little hard is just everything in Ethos is very tightly coupled, and so we don't want to release components when all their dependencies aren't sort of fit for outside consumption, kind of with code quality and all that. Okay. But other than that, it should be available soon, hopefully this summer, and I guess I'll take any questions. Yes.
Should I just shout it? So, do you have any support for, like, supporting infrastructure for getting stuff in languages like from outside of Ethos, outside of the Ethos ecosystem, so to speak, like into the ETN, the eNotation?
Yeah. So, this is where perhaps I should have given the caveat right up front, right? And I think I did a better job of this last year, but Ethos is 100% clean slate, okay? So we make no attempt to say that we're going to support HTML. We make no attempt to say we're going to, So yes, basically you have to, but the system calls are so different than POSIX anyway that you can't just easily port an application. You really have to rethink.
I was thinking network protocols.
And even the network protocol, we use a protocol called Minimal. So we envision there could be gateways that would transform between the two. But I mean, in a certain sense, we could see we're kind of trying to take things as far as we can to see where it goes. And the big trade-off we made is let's just go clean slate and see what happens. And I think we got some interesting results that if, not everybody's going to be using Ethos someday, but we think they'll be using something that resembles Ethos in its kind of idea of simplification through. And I guess another way to look at it is we're trying to take responsibilities away from the programmers because they already have enough balls to juggle, to have to worry about things like recognition. Although it's so important that it should be just made universal, and then they don't have to worry about it as much. Okay, at least that's what we think. Okay. Anything else? Okay. Thank you.